co-NP and the asymmetry of NP. As a further perspective on this general class of problems, let's return to the definitions underlying the class NP. We've seen that the notion of an efficient certifier doesn't suggest a concrete algorithm for actually solving the problem that's better than brute force search. Now here's another observation. The definition of efficient certification and hence of NP is fundamentally asymmetric. An input string S is a yes instance if and only if there exists a short t so that B of st is equals to yes. Negating this statement, we see that an input string S is a no instance if and only if for all short t, it's the case that B of st is equals to no. This relates closely to our intuition about NP. When we have a yes instance, we can provide a short proof of this fact. But when we have a no instance, no correspondingly short proof is guaranteed by the definition. The answer is no simply because there's no string that will serve as a proof. In concrete terms, recall our question from section 8.3. Given an unsatisfiable set of clauses, what evidence could we show to quickly convince you that there is no satisfying assignment? For every problem X, there is a natural complementary problem X bar. For all input strings S, we say S is in X bar if and only if S is not in X. Note that if X is in P, then X bar is in P. Since from an algorithm A that solves X, we can simply produce an algorithm A bar that runs A and then flips its answer. But it is far from clear that if X is in NP, it should follow that X is in NP. X bar is in NP. The problem X bar rather has a different property. For all S, we have S in X bar if and only if for all t of length at most P of the size of S, B of st is equals to no. This is a fundamentally different definition, and it can't be worked around by simply inverting the output of the efficient certifier B to produce B bar. The problem is that the exists t in the definition of NP has become a for all t, and this is a serious change. There is a class of problems parallel to NP that is designed to model this issue. It is called natural enough co-NP. A problem X belongs to co-NP if and only if the complementary problem X bar belongs to NP. We do not know for sure that NP and co-NP are different. We can only ask, does NP equals to co-NP? Again, the widespread belief is that NP is not equals to co-NP. Just because the yes instance of the problem have short proofs, it is not clear why we should believe that the no instances have short proofs as well. Proving NP is not equals to co-NP would be an even bigger step than proving P not equals to NP for the following reason. 8.26. If NP is not equals to co-NP, then P is not equals to NP. Proof will actually prove the contrapositive statement. P equals to NP implies that NP is equals to co-NP. Essentially, the point is that P is closed under complementation. So if P is equals to NP, then NP would be closer under complementation as well. More formally, starting from the assumption that P is equals to NP, we have if X is in NP, which implies that X is in P because P is equals to NP, then which also implies that X bar is in P, which also implies that X bar is in NP, which implies that X is in co-NP. And X is in co-NP, which implies that x bar is in NP, which implies that x bar is in P, which implies that x is in P, which implies that x is in NP. Hence, it would follow that NP, which is a subset, equals to co-NP, and co-NP is a subset equals to NP, whence NP is equals to co-NP. Good characterizations. The class NP intersect co-NP. If a problem X belongs to both NP and co-NP, then it has the following nice property. When the answer is yes, there is a short proof, and when the answer is no, there is also a short proof. Thus, problems that belong to this intersection, NP intersect co-NP, are said to have a good characterization, since there is always a nice certificate for the solution. This notion corresponds directly to some of the results we have seen earlier. For example, consider the problem of determining whether a flow network contains a flow of value at least v for some quantity v. To prove that the answer is yes, we could simply exhibit a flow that achieves this value. This is consistent with the problem belonging to NP. But we can also prove the answer is no. We can exhibit a cut whose capacity is strictly less than V. This duality between yes and no instances is the crux of the max flow mean cut theorem. Similarly, Hall's theorem for matchings from section 7.5 proved that the bipartite perfect matching problem is in NP intersect co-NP. We can exhibit either a perfect matching or a set of vertices A, which is a subset equals to X, such that the total number of neighbors of A is strictly less than the size of A. Now, if a problem X is in P, then it belongs to both NP and co-NP. Thus, P, which is a subset or equals to the intersection between NP and co-NP. Interestingly, both our proof of the max flow mean cut theorem and our proof of Hall's theorem can hand in hand with proofs of the stronger results that maximum flow and bipartite matching are problems in P. Nevertheless, the good characterizations themselves are so clean that formulating them separately still gives us a lot of conceptual leverage in reasoning about these problems. Naturally, one would like to know whether there is a problem that has a good characterization but no polynomial time algorithm. But this too is an open question. 8.27. Does P equals to NP intersect co-NP? Unlike questions 8.11 and 8.25, general opinion seems somewhat mixed on this one. In fact, this is because there are many cases in which a problem was found to have a non-trivial good characterization, and then sometimes many years later it was also discovered to have a polynomial time algorithm.